Hello students, this lecture is about the Maxwell fourth equation, and in this lecture you will come to know that what exactly the Ampere's law and how the Maxwell has modified the Ampere's law and finally derive this Maxwell equation. So first of all we shall start with the discussion of Ampere's law, and then we see what is the correction made by the Maxwell in the Ampere's law, and we finally understood this equation. So first we shall open up with the Ampere's law. Ampere's law is exactly what? It's very simple. Whenever there is a current inside the conductor, as you are able to see that this is the current carrying conductor, the magnetic field is generated around that conductor. Okay, and Ampere has given us the simplest way to calculate that magnetic field by using this equation. The equation is line integral of magnetic field B dot dl is equal to mu naught I, where mu naught is the permeability of the free space and I is the current. So here the students are able to easily understand the concept that the current is flowing through the conductor, the magnetic field gets generated around the conductor, and we are getting the calculation of the magnetic field. If you solve this line integral, you are able to calculate the exact value for the magnetic field around the current carrying conductor at any point. Okay, so this is the simplest Ampere's law which you studied at the high school. Now let us see what is the modification in the Ampere's law. Now let us move to the slide number 40. Here the students are able to see that as per the Ampere's, when we are calculating the current around the current carrying conductor, when we are calculating the magnetic field around the current carrying conductor, we are able to see that the circuit has to be closed. Here the students are able to see that the line integral, this S1 is closed. Closed means only the circuit should be connected. But in case of the capacitor plates, here the students can see that there is a gap. There is a gap between the capacitor plates. And when we are trying to calculate the magnetic field in the region where the capacitor plates are placed, as per Ampere's law, the magnetic field has to be 0. Okay, but in the region S1, the magnetic field has some value. So in capacitor plates region, Ampere's law is basically giving us the 0 magnetic field as per the law where that line integral has to be closed. But the capacitor plates are open. In that sense, that means Ampere's law is not fully justified the concept of magnetic field in the capacitor plates. However, when we are calculating experimentally, we are getting the magnetic field around the region S2 also. Okay, so Ampere's law is not fully justified in the regions of capacitor plates. So what the Maxwell did, Maxwell basically done the correction in the Ampere's law by giving some modification in the Ampere's law by adding the displacement current in the discussion of the Ampere's law. So let us see with the help of a simulation that what exactly I am basically trying to convey you. So here the students are able to see when we are having the current carrying conductor, the magnetic field is looping around that conductor. And when we are shifting the discussion to the capacitor, let us move to the capacitor. So still we are getting the magnetic field around the capacitor, right? So we are getting the magnetic field around the current carrying conductor, and as well as we are getting the magnetic field around the capacitor plates. So here there was some correction that was required in the Ampere's law. So Maxwell himself did that correction, and he has justified the relation by adding the term displacement current in the equation, that we can find out the magnetic field around the capacitor plates where the circuit is not closed. Only the time varying electric field is basically responsible for that magnetic field that is coming around the capacitor plates. So let us move back. So when we move to the next slide 41, we are able to see that this is the correction term that is being added by the Maxwell. What is the correction term? ID, that is the displacement current, is equal to change of electric flux. Right? The change of electric flux is basically generating the displacement current, and Maxwell corrected the Ampere's law by adding this displacement current term in the expression. So now the new modified Ampere's law has become B dot dl, line integral of magnetic field, is equal to mu naught I plus ID. ID is the displacement current added by the Maxwell, which is showing that the changing electric field as a source of magnetic field. In the equation of third equation of Maxwell, we learn about that the changing magnetic field as a source of electric, and in this equation what we learn, changing electric field as a source of magnetic field. What it means, we are again trying to unifying the theory. We are not taking the electric and magnetic field separately, it is unifying. Electric is because of magnetic and magnetic is because of electric. So this is the clear cut proof of that discussion, that changing electric field as a source of magnetic field. Okay, now let us continue and we move back to the Maxwell fourth equation, slide number 75. So here the students are able to see, as per the Maxwell that Ampere's law, that the line integral of magnetic field is equal to mu naught I plus ID. This ID is the correction term added by the Maxwell himself, that then basically during the capacitor plates, as we have seen earlier, that the changing electric field as a source of magnetic field. Okay, so the correction term is epsilon naught. Epsilon naught is the permittivity of the free space, and d phi E by dt is basically representing the change in the electric flux. Okay, so now we know the simple terminologies, that the current is linked to the current density, which can be written as I is equal to J dot ds. Flux of electric field can be written as E dot ds, followed from the Gauss law. So we are substituting I and phi E in this equation. Okay, and on rearranging, the equation finally becomes B dot dl is equal to mu naught I is being replaced with current density J dot ds, which finally it can be written as mu naught epsilon naught d phi E by dt, and phi E is being replaced with E dot ds, which is the electric field. Okay, move to the next slide. So what we are going to do over here, we are just replacing this term epsilon naught E as electric displacement, which can be written as D. D is electric displacement. So we are substituting D as epsilon E. So this equation can be rewritten as B dot dl mu naught J dot ds mu naught d by dt, and this epsilon E can be written as D, which I have already described, dot ds. Now we are taking this mu naught common from these 2 points and taking on the left hand side. When we are replacing it as B by mu naught, so it can be written as finally H, which is the magnetic intensity, and H dot dl J plus curly D by curly D dot ds is our final equation. Okay, now let us see that on the left hand side we are having the line integral, and on the right hand side we are having the surface integral. So we are going to take the help of the Stokes theorem here. Move to the next slide. So when we are applying the Stokes theorem on the left hand side of the equation, the line integral can be replaced with the surface integral, but what is the condition? Curl of H. Curl of H if we are writing, so we can convert the line integral into the surface integral, and the final equation will become curl of H J plus d by d dt dot ds. So on rearranging, we are getting the final equation as curl of H is equal to J plus curly D by curly D. This is the Maxwell fourth equation, and what it signifies, that the changing magnetic field as a source of changing electric field as a source of magnetic. And in the previous equation, what you learned, the changing magnetic field in Maxwell third equation as a source of electric, and here what you learn, the changing electric field as a source of magnetic.